this class we are going to now talk about little bit advanced concepts, like where you cannot use for like simple beam theory for calculating the stiffness constant, etc. Now for that, before we go to that, we will just brush up little bit about the whatever the basics we have learnt and some more things which will be required for this study. Okay. So now you know that according to laws of elasticity, stress and strain are linear, right? So if the sigma is the stress and let us say epsilon in the strain, then we get a linear curve. Now what is the area under this curve is half into sigma into epsilon, and this is also known as the strain energy. Okay, this is also known as strain energy. So now let us say I have some body, okay, and in that there is some element, volume element dV, which is having its stress as sigma and strain is epsilon. Then half sigma epsilon is the strain energy density of that particular body, and then strain energy density. Now to calculate the total strain energy, let us say we call it SE, total strain energy is equal to strain energy density, that is half of sigma epsilon into and then we have to integrate it over the volume. So this is a volume integral of half sigma epsilon dV. Now this half sigma epsilon you can also relate it with the spring mass system, because for a spring mass system you know that let us say you have a spring of spring constant K and any mass m is there, and let us say the deflection is x. Then while it is at a deflection x or stretch till x, then the energy stored in it is equals to half k x square, and this you have already learned probably in 12th standard or some basic mechanics course. And now you can see that here half, you can write it as half into kx into x, where this kx is the force and this is the deflection. So this is like the sigma and this is the epsilon, right? Okay. So total strain energy SE is equal to integral 0 to volume half into sigma epsilon dV. Okay. Now we will discuss a theorem called Castigliano's theorem. So this is very specific to mechanical engineering, and in this part of the course or in the scope of this course we are not going to discuss what is there in Castigliano's theorem and how exactly that is derived and etc. But we are going to use the theorem like the result of this theorem, okay, and because that will be useful for us for solving different complicated beams. So what does this theorem say? Theorem says is force at the direction x is equals to partial derivative with respect to deflection at that in that direction of total strain energy expressed as a function of deflection. So here ux is deflection in x direction and fx is force in x. Okay. So this is one of the expression, and the second expression is just the vice versa, that is ux or the deflection is partial derivative with respect to the force, while total energy, total strain energy is expressed in terms of the force. Okay. Now these two expressions we will use for solving our solving different complicated structures, but we are not going to discuss that how these two expressions come. Okay. Before we go to that exactly how we apply this theorem, okay, we will consider the one of the constant which we discussed in last class, that is guided beam. So if you remember, guided beam was the case where one side is fixed and another side was moving without any rotation at this end or any movement in this direction. Okay, only this end is left side or this end is fixed and this end is moving, but only in this direction, up and down. Okay, so it is something like this. So let's assume that this side is of the cantilever is fixed, and then this is the mass which is connected to the other end, and that mass is moving only in this direction. Okay, so there is no x-axis movement or no rotation in the frame. Now for that we have seen the, if we draw the free body diagram, then the constants are like this, right? Left side is fixed, so anyway there will be all the different reaction forces, R1x, R1y, and then we have the moment m1, and this direction actually we are applying the force. So we have the force F, which is an external force, and then the reaction force R2x, and then M2, and the reaction moment. Now you see that in the y direction we have not mentioned any, for this end in the y direction we have not mentioned any reaction force, because in that direction the mass can move, so there will not be any reaction force. So by balancing all the force, we can write that summation over Fx or equals to R1x minus R2x equals to 0. Then summation over Fy equals to R1y plus F equals to 0, and then summation over moment mz equals to minus m1 plus m2 plus fl equals to 0. Now see here I have put a negative sign before m1, because here I am considering that the clockwise moments are negative. So this is pure convention, whatever convention we fix, and accordingly we should move with that particular convention, we should not change it. Okay, so for this purpose I am considering only that anti-clockwise moments are positive and clockwise moments are negative. Now, and another thing is, let's assume that the beam length is L. Okay, so this distance is L. So minus m1 plus m2 plus fl is equal to 0, right, because this force will have a moment of fl, and m2 and fl are both in the same direction, that is anti-clockwise, and both are positive. Okay. So now we are going to discuss what are the boundary conditions. Okay. So let's see the boundary conditions. For this particular boundary condition, we can write that ux at x equal to L is equal to 0, right, and then dw dx at x equal to L equals to 0. So what I am considering here, that x direction the deflection is u, and y direction the deflection is w. Okay. So this is u and this is w, and this is my x and y. And how are we getting that? We are getting that because u at x equal to L, x equal to L means this point here, right, and in at this point we don't have any movement in the x direction, right, we don't have any movement in the x direction. So at that point, or at the tip of the cantilever, the x directional deflection is 0. And then another thing is, as this is guided beam, as I am saying that there is no rotation. So guided beam, no rotation means you can see that there is also no slope. So this is in this direction, or the y direction, the deflection is w. So what is the slope in that direction? It is dw dx. So dw dx, and dw dx at x equal to L will be 0. These are two boundary equations. So now we see that what we get this boundary equation from these boundary equations in terms of Castiglione's theorem. Now, according to Castiglione's theorem, we see that ux is equal to del del fx of the strain energy, right, in terms of fx. Now, what is this fx? Fx is the force in x direction, force in x direction, right. Now, what is the force in x direction at x equal to L? That is the reaction force R2x. So ux for x equals to L is equal to del del R2x of strain energy, same here R2x, okay, and this equals to 0 according to our boundary condition 1. Then what is the another condition? Another condition is that dw dx. Now dw dx is what? dw dx is the slope, right, and this slope means the angle theta. And what does it make angle theta? The moment. So if the force makes deflection and moments makes the body rotate, right. So dw dx, this dw dx is the slope of the beam, right, and dw dx means some angle, let us say theta. If theta is the deflection, then what is the force? Force is the actually the moment, right, and at x equal to L, what is the moment? That is m2. So according to Castiglione's theorem, del del m2 of strain energy in terms of m2 is equal to 0. Okay, now you need to calculate what is the strain energy. So strain energy SE equals to SE axial plus SE bending. Now here I would like to point out one earlier case. While the cantilever transverse force deflection we have calculated, there you see, here you can see that this is the case where it is pure bending. So there is no lateral deflection associated with it, right? Neutral axis, and according to the neutral axis is pure bending case for this transverse force cantilever, right? But here what we are considering now, we have axial stress also and transverse stress also, because this is guided case, and then we have to calculate the strain energy for both the cases. So first of all we will calculate one by one, that is strain energy axial and strain energy bending. So what is strain energy? Strain energy is half into integral of 0 to v sigma ax epsilon ax dv plus half of again volume integral 0 to v sigma bending epsilon bending dv. Okay. Again we know that sigma by epsilon is equal to y. So what I can write is epsilon equal to sigma by y. So here we can write that half of 2y into 0 to v sigma x square dv plus half of y also comes out 0 to v sigma bending square dv. Now 1 by 2y to 0 to v, this is sigma x. Sigma x means the stress in the axial direction, right? Now axial direction, what is the stress? It is the force in the x direction divided by its area. So let's assume the force at any point x in x direction is px, okay, then it will be px by a whole square dv, or we can write dv as a dx. Why? Because this is our beam and this dv is like this cross section, okay, and here this is x direction, let's say, and this is y direction. Now see that at different position of the beam there will be different force, but area throughout the beam is same according along its length, the area is same. So a is a constant, right? So this dv we can write as a into dx, where a is the area of this volume, this small volume, and dx is this dx. And then we have 1 by 2y 0 to v sigma bending and square. Okay, fine. It is again 1 by 2y and one of the a's goes off, so it is 1 by 2y a. As it is constant, I take it out. Now this volume integral becomes a line integral, and then it is limit will be 0 to L, because L is the length of the beam. And here for sigma bending we will refer to one of the earlier result what we got. For this bending case, pure bending case, we got that from a distance z from the neutral axis, the stress is Ez by rho, where E is the Young's modulus, z is the distance from the neutral axis, and rho is the radius of curvature. And then also we got that 1 by rho is equals to m by EI, which is like m is the moment and E is the Young's modulus and I is the inertia. And if we combine these two, then we get that sigma x equals to m0 z by I. Now we are going to use this relation for our current solution. So m0 z by y, where m0 was the moment and z was the deflection from the neutral axis, and here in this case we are considering this as w, right, because in y direction or in the vertical direction we are considering the deflection as w. So now let us use this relation for our present solution, and what we got? We got that sigma is equal to m0 z by I. Here in y direction, let us say if the deflection is, or let us say if we take a point where the layer is at a distance small y from the neutral axis, then we can write that by 2y, this y is the Young's modulus capital Y, and then 0 to v. This sigma is m0 by z by I. So m0 is here our general m, or the moment at any point x. So m, and then the z is actually here let us say y, because we are taking the layer in y direction. So let us say at a distance of y from the neutral axis, like small y, at a distance of small y, we can take that my, and then I is same. So my by I square into dv is dA dx, right. Now this part is same, I keep it like that, and this part 1 by 2y, this volume integral I can break it into two parts. One is line integral 0 to L and another is surface integral 0 to A, okay. And then we have m square by I square y square dA into dx. Now this part is again same, and this part is 1 by 2y, again 0 to L. I can write the m square by I square, m square by I square I take it outside, and then we can write that 0 to A y square dA into dx. This 0 to A y square dA integration is the area moment of inertia, right. So this will give me I. So equals to, then again the first term as it is I wrote 1 by 2y ya into 0 to L px whole square dx plus 1 by 2y, y is the, here the first capital Y is the Young's modulus, into 0 to L m square by I square into this is I dx, right. So this I will cancel from numerator and denominator, and then we will get 1 by 2ya 0 to L px and dx plus, so I can take the I out because this is a constant, 1 by 2yi 0 to L m square dx. Now this expression is important, and we will just calculate here what are the values of px and m for different x's, and then we can calculate the total strain energy. So how we know px? From the free body diagram we can get. So this is the free body diagram. You see that the r1x, r1y and r2x f everything is drawn here. So as per our first condition, that sigma fx equal to 0. So r1x minus r2x equal to 0. That means my px is equal to ultimately r1x equals to r2x, because there is no other force in x direction and it is the same force at every point. Okay. Then mx or moment at any point x will be equals to minus m2 minus f into L minus x, right? Because if I take moment with respect to this point, with respect to the leftmost point, which is the fixed point, then m2 will be there, and along with that, like let's say the point is at a distance x, at a distance x from the left end. So that from that point, this force F is at a distance x minus L, sorry, L minus x. From that point, this force F is at a distance L minus x. So that moment for that force will be L minus x. So the mx, which is actually in this direction, so it will come as negative, right? Mx equal to minus of m2 minus f into L minus x. Now putting these two equation, that is px equals to r2x and mx equals to minus of m2 minus f into L minus x. We put these two equations in the strain energy expression. We get strain energy equals to r2x square into L by 2ya plus m2 square L 2yi plus m2 to f of L square divided by 2yi plus f square L cube divided by 6yi. So this you can get by just putting the m values and the r2x and integrating it. Now we need to calculate the partial derivatives of strain energy. So first is, let's say we derive it with respect to derivative with respect to r2x and m2. These are the two terms we need to do, right? If you go back, then you see that this is from our boundary condition and strain energy expression, we got that ux equal to del fx of strain energy, and which is equals to 0, and dw dx is equal to del m2 of strain energy, which is also 0. So delta SE by delta r2x equals to 0 implies that r2x equal to 0, because in this strain energy term, the only term which depends on r2x is the first term, r2x square L into L divided by 2ya. The other terms are independent of r2x, so that will become directly 0. Okay. Now delta SE divided by delta m2 equals to 0, and again if we partial derivative it with respect to m2, then the first term will become 0 and the second term will give me 2 m2l at 2i. So it is m2l into m2l divided by only yi, 2 cancel off, and then plus FL square divided by 2yi. So FL square plus 6yi, this term will also become 0 with respect to partial derivative with respect to m2. So this is 0. So then from this expression we can get that m2 equals to minus of FL by 2. Again from our another condition was there, that is sigma mz equals to minus of m1 plus m2 plus FL equals to 0. So now m2 is equal to minus FL by 2. So now we can write that m1 equals to plus FL by 2. Now once we got the m2 and m1, though m1 is not required, but anyway for continuity we just calculated m1 also. Now we got m2 and m1 both, so we calculate the strain energy again in terms of force then. So strain energy is equal to R2x is there, right? R2x is 0, so it becomes 0, and then we have m2 is FL by 2, m2 is right, m2 is minus FL by 2. So strain energy is equal to m2 means minus of FL by 2 whole square into L by 2yi plus minus FL by 2 into FL square divided by 2yi plus F square L cube divided by 6yi, and in all the cases I get this is 8yi minus square L cube divided by 4yi plus square L cube divided by 6yi, right. So if we take it common, then F square L cube by yi equals to 1 by 8 plus 1 by 4 plus 1 by 6. So calculating we get that the total strain energy is now in terms of F square L cube divided by 24yi. Now we need to calculate the deflection actually. So that is the W, right. So W deflection is because of which force? F, right. So W at x equal to L is equal to del del of force F, because F force is acting at the tip of the cantilever, that is at x equal to L, and that is causing the deflection of the tip, that is the W. So W or the deflection equals to del del F of the strain energy as per Castigliano's theorem. So that is then 2F L cube divided by 24yi. So that is equals to F L cube divided by 12yi. So now we know the deflection. So force by deflection or the stiffness of this guided beam, let's call it KB, or the stiffness of the beam is equal to F by W equal to 12yi divided by L cube. So this is one of the important relation.